Okay, so this is where we stopped. So again, to search for an entry in this table, I have to do a binary search on the index and then follow these two pointers. The pointer that points to the block that I identified, the value that I identified, and the next block. Read all the blocks in between these two pointers. Yeah, that's all I have to do. And that gives me all the records that I'm looking for. Okay? What about insertion and deletion? If I want to insert a new record, it's expensive, of course, right? I have to locate the block for which the record should be inserted. So let's say I want to insert a record with value 4. I'll have to locate this block. I realize it's full, so I have to, put things here, make an empty space, put a 4, update the records here, or update the pointers here, and so on. So I really have to maintain the file and the index, and it's expensive. Okay. Deletion is also expensive because I have to find the record, and then if I have empty spaces, I have to push up and update that. Yeah. So really maintain. Whenever I have a file that is sorted physically on disk, it becomes very expensive when it comes to updates, insertion, and deletion. And that's why in practice, most of the time, even though this is allowed in databases, most of the time you don't tend to sort the file physically on disk. You leave it unsorted and use an index on top of it, which is the type of index we're going to talk about next. Okay. Questions? Good. For clustering indices, I can improve insertion. What's that? Let me mute everyone. Okay. So to improve insertion and deletion time for a clustering index, I can reserve a whole block or a cluster of continuous blocks for each value of the clustering field. Okay, let's see what this means. Here's an example of a clustering index with reserved blocks. Let's see why is it different from the previous one, and how does this improve insertion and deletion time. Okay. So I have as before, right, for every distinct value, I have a block entry. Okay, so 1, 2, 3, 4, 5, 6, 8, and then the pointer points to the block with the first value, with the record with this, for the first record with this value. So I have for value 1, pointer to block 1. For value 2, pointer to block 2. Why? Because now this is the block that contains the first value 2. Okay. Now, if you notice, I'm leaving some empty spaces per block. So I'm reserving every block to contain only records of one certain value. So the first block is reserved for records of value 1, right? And I have additional block pointer here, which tells me if this gets full, so I have, I filled this with employees in department 1, you create another block and then point to it and then add more records of, employees of department 1. And you keep doing this. So every block is reserved, or a set of blocks are reserved for one particular department. Yeah. So if you look at this, for instance, department 3, you have 2 blocks here. Yeah. So all the records here are for department 3, and this got full. So I created a new block. I inserted a record here of value 3, and then the rest of the block is empty. So if I now need to insert a new record with department equal to 3, I just have to insert it here in this block. Yeah. And once this block becomes full, I allocate a new block and point to it using this pointer. So the null pointer becomes a pointer to the next block. Yeah. So it's a chain of blocks that are reserved for a particular department. That speeds up insertion and deletions drastically. Why? Because now all I have to do is do binary search, allocate the block, and if there is an empty space, insert the record. If there is not an empty space, allocate another block and point to it. Yeah? So that's faster in terms of insertion. In terms of deletion, again, allocate the block, delete. If there is an empty space, keep it, because I want to have some empty space in blocks for later insertion. If a block becomes empty, you just remove it. So, you know, and set the pointer to null. Yeah, the block pointer from the previous block to null. And so it speeds up insertion and deletion drastically, this idea of chaining of blocks. Okay? Questions? What about searching? If I want to search for the record 4, find all the the record 6. Find all the records with department number equal to 6. What do I have to do? Binary search on the index that tells me follow this pointer. I follow this pointer, read this block, and then I realize, oh, there is a block pointer here that is not null, so I follow it and read the next block. And then here I realize the block pointer is null, then I'm done. I've read all the records with department number equal to 6. Okay, that's really the key point here. Okay, questions? Good. Okay, so we talked about primary indices, which are the file is sorted physically on disk, and it's the indexing field is a key field, so it's unique. And then we talked about clustering indices, which are the file is physically sorted on disk, but the indexing field is non-key, so it's not unique. Then we're going to talk about secondary indices. That's really the most popular type of indices you see in database systems. A secondary index provides a secondary means of accessing a file. Okay. The data file could be ordered, unordered, or hashed, so it doesn't matter what is the file organization, whether the file is ordered physically on disk or not, it doesn't matter. You can create always a secondary index on any table, whether it's sorted physically on disk or not. The secondary index key, right, can be, or a field can be a key or non-key field. Yeah, so it could be unique or non-unique. You could also create many secondary indices on the same file. One question for you: can I create how many primary indices can I create on a file or on a table? Before I take this question from the chat, but how many primary indices can you create per a file or a disk or a table? Can I create multiple primary indices or multiple clustering indices on a table? The answer is no, of course. Why? Because the file has to be physically sorted on the field. So can I physically sort a file or a table using multiple fields at the same time? So, you know, have the table sorted on name and also sorted on SN, or sorted on name and also on department number. I have to choose one ordering field, yeah, to sort the file on it. I don't understand your question, Stephanie. So in which the question is referring to which slide? Or referring to which type of index? Clustering?
So I'm referring to the slide where we're using a pointer. Yes.
This one, yeah?
This one.
Okay. So tell me, what is the question
so
again?
Now the blocks are not consecutively stored. This is what I mean. No, no, we're avoiding the cost of having to search through like records that we don't want, but we're getting the cost of going like on the disk, finding the block, which is expensive, right?
Not exactly. So here's how I would do the search. I would do binary search on the index. Okay, so to locate the block pointer of the correct value. So that's not expensive, yeah, because this file is small and it's sorted. So you agree with this? Just did a binary search here. Follow the pointer. So let's say I'm looking for value 3. Follow the pointer of 3. I read this block. So I read one block, and then follow this pointer to the next block. That's 2 blocks, and then find the null pointer here. So I stop. So I really didn't do any, you know, unnecessary reads of any blocks that I don't need. All I had to do was do, yeah.
I mean, when I find a block that has, like, it's filled with all the threes, and I have to create a new block of threes, wouldn't it be at the end of the table, like after the 8, and would be?
No, it's not going to be like this. It's going to be right somewhere, like really randomly on disk. But I have a block pointer. So I see your question, right? But the block pointer helped me to get to it directly. So this block pointer, you see this block pointer?
Yes.
Yeah, basically it will point to the block immediately. So I don't have to read all of these blocks to get to the block. I just follow this pointer. What does a
I don't have to read all the blocks, but I mean it's not consecutively stored. So I mean, and I have to sorry, incur the expense of going to another place on disk. This is what I meant.
Yeah, you have to go somewhere else. Yeah, so it's not going to be physically stored on this value. Correct. Yeah.
Thank you.
You're welcome. Okay. So to answer my question, you cannot create more than one primary index or more than one clustering index on a table. Yeah, only one. One is allowed. Basically, you can create one primary index or one clustering index, and that's it. Yeah. You can create multiple secondary indices. Why? Because the file doesn't have to be physically sorted on the indexing field. So you can create multiple of them at the same time. Okay, so we're going to look at different types of secondary indices, and then we'll be done for today. Okay, so we have first start on a secondary index on key fields. What does it mean, key fields? It means that the column or the attribute is unique, right? There is no repetition inside of it. You don't have two records with the same value for this field. And I want to create an index on this field. Okay, and it's non-ordering, meaning that the file is not ordered on this field. Otherwise, it's not a secondary index. It will be a primary index. Like, I'm better off creating a primary index. Okay, so the file is not physically sorted on this field. Yeah, it's key, it's unique, but the file is not sorted on it. Okay, the index would look like this. It would have the values of the key. Yeah, so every key you would have a value or an entry for it in the index, and then the second would be a block pointer or record pointer that points to the block which contains the record. Yeah, it's a dense index because you have per record and entry. Let's see an example. Here's an example. So here is a table, and I have some field here. This field is unique. It's a key. Obviously, there's no two records in the table with the same value. So if you look at it carefully, you don't have any repeated values. So it's a key. It's a unique field. Okay. Is the file physically sorted on it? Okay. From the diagram, do you see that the file is physically sorted on this field? The answer is no, obviously, right? You have 9 appearing before 5, 13 before 8, 7 after 12, and so on. So the file is not physically sorted on this field, okay? But I can create a secondary index on this field, right? Because it's key and it's non-ordering field. Okay, so how does the index look like? You just create an entry per record. So I have 9, we'll put it here. Remember that the index has to be sorted. So all I have to do is put these values in sorted order in the index, and then add a block pointer to the block that contains the record with this value. So 1, what is the block that contains 1? It's this pointer, right? If I follow this pointer, it points to this. 2, it's this, right? The pointer that points here, and so on. So every record, right, or every entry here will just have a block pointer that points to the block that contains the record with this value. That's all I have. Okay, so it's very simple. Why does this save me time? So how is this index helpful? Anybody can answer this?
Since the index, let's say the index field value, it's easier than to find the indexing field. لأنه they're sorted ومحطوطين محطوطين بقلب الديسك قراب من بعض. It's easier, it's faster to navigate through them.
As you said, and somebody on chat also said, right? So I have the index, it's sorted, so I can do binary search. So let's say I want to find the value 13, all I have to do is do binary search on this index, okay? And that's much faster than doing linear search on this table, because since the file is not sorted on this field, I have to do linear search. I can do anything else. So I can do binary search on the index. The index size is much smaller, so I'll read fewer blocks. And also, once I have the value, all I have to do is follow the pointer to get to the record. Here I have 13. I'll follow this pointer to get to this block. Yeah, so it's much faster than doing a linear search on the table. Insertion is efficient, exactly. Abid Haj, right? So insertion is really efficient here. Why? Because the file is not sorted. So all I have to do is what? Is figure out, let's say I want to insert a new record, all I have to do is, create a new block and put the record in it, and then just, add the entry in the index. So the index needs some maintenance, of course, right? Because it has to be sorted, and just add a pointer to it. So definitely the insertion and deletions is faster here than in the case of primary and clustering indices. Similar to a stack. I don't see this very well, but it could be. In what way? You want to explain in what way? You mean in the insertion? You insert it at the top? Okay, yeah, makes sense. Okay, but the key point is that it makes it a lot faster to search, because without the index, I would have to do linear search. With the index, I can do binary search because the index itself is sorted. Yeah, so this really saves a lot of time. Okay. Okay, let's do some exercise to just do the math, make sure that, right, it really helps with the number of blocks. Okay, so again, assume that the record size is 100 bytes.
Professor, sorry, I'm أتشك. Is it possible to index the block pointer? يعني تكون two levels, an index value,
yes,
field value.
This is what we're going to do. We're going to generalize it in the next lecture to multiple. Yeah.
Okay. Yeah.
So this is really what is done in practice. Okay. Okay, let's do some mathematics. So suppose you have the record size is equal to 100 bytes. The block size is 1024 bytes as before, and the number of records is 30,000. Okay. Then assume, right, unspanned organization as before. So no records span 2 blocks. The blocking factor is going to be 10 records per block because I have 1024 bytes divided by the size of the record, which is 100. That's 10 records per block. These calculations are important. Yeah, expect something similar in the exam. Okay. Number of file blocks is equal to 30,000 divided by 10. That's the blocking factor. You get 3,000 blocks. So in total, I have 3,000 blocks to store the file. Our file. This table needed 3,000 blocks. To get a record, I would have to do only linear search. I can't do anything else, right? Because the file is not sorted on this field. So I have no option but to read the block from the beginning, keep checking every block until I find the record I'm looking for. Okay, so then I would have to do linear search, and that's on average 15,000 blocks to read. 3,000 by 2 divided by 2. Assuming that the record is midway through the table on average. Okay, with the index, assume that the field, right, is size is 9 bytes and the block pointer is 6 bytes. Then the index entry in total is 15 bytes. The index blocking factor is 68 entries. So 1024, the size of the block, by 15 bytes, that's 68 entries. Meaning what? Meaning that I can store 68 of these entries in one block, yeah, compared to 10 records per block. Okay. So I can store much more entries inside the block index entries than records. Okay, so how many entries do I have in the index? I have exactly the number of records. I have 30,000 records, and there is an index per entry per record because it's a dense index. So I get 30,000 entries. So how many blocks do I need? I have 30,000 entries divided by 68 entries. That's 442 blocks. So in total, I have 442 blocks that I need for the index versus 3,000 blocks that I need for the table itself. Okay. How do I get a record? How many blocks would I need to read to get to a record? It's exactly log 442 to the base 2 because I can do binary search on the index. It's sorted, so I'll do binary search. I do log 442. That's 9 plus 1 block from the data file. Yeah, because I will do binary search here. That's log the number of blocks, log 442. That gives me a particular entry here. Then I follow the pointer to get to the record. That's one additional block. It's 442. Why is it typo? Why, Georgie? Divide 30,000. Let's divide it. 30,000 by, let me check. Calculator. 30,000 divided by 68 is 441.17, right? No, Georgie, can you turn your mic on and tell me what you mean?
Yeah, I meant here in ceiling of log base 2 of BI, when they took the number of BI, they took it as 441.
Yeah, it's typo.
While we have it as...
Yeah, it's log 442.
Okay, perfect. Thank you.
You're welcome. Yes, it's a typo. Okay. So I have 10 blocks on average versus having to read 1,500 blocks. I hope you see the huge difference in performance when I created the index versus when I don't have it. Yeah, huge improvement in performance once I have index. And that's why you really in practice need to use indices. Okay. We're going to talk about another type of secondary indices in which the field, indexing field is not key. What does it mean? It means it's not unique. Yeah, you have multiple values. You could have multiple values, the same value per multiple records. That's what I mean by a non-key field. Okay, again, the file is not sorted on this field and it's not unique. So we have several options to implement such an index, yeah, a secondary index on this field. You can include duplicate index entries with the same value, one for each record. So repeat the values and then have one entry per record. That would create a dense index. Or you could keep a list of pointers in the index entry, or create an extra level of indirection to handle the multiple pointers. That's what somebody was asking me, which is doing a multi-level index views. Yeah, let's see what I mean by this. So let's say I have the department number, right? That's the field I search on a lot, and I want to create an index on this field. Why? Because I use it a lot in queries, and obviously the table is not sorted on this field. If you see, right, department 1 appears here, then appears here, and appears here. So the table is not sorted on this field whatsoever, and it's not key. You have repeated values here. Yeah, so multiple records of employees in department 1, and so on. So what is the candidate for this? A secondary index. So it can't create any other type of index on this field because the table is not sorted on this field and the field is non-key. Okay. So here is one way of creating the index. I create a top level index which contains the unique values for department numbers. So I have 1, 2, 3, 4, 5, 6, 8, and then a block pointer to a block of pointers. And that contains record pointers to the records that have this value. So here's 1, I have a pointer that points to this block of pointers, and this guy points to all the blocks that were all the records that contain the value 1. So it has this one, and then this one, and a pointer to this one, and so on. For the value 2, I have a pointer that points to a block which contains, right, pointers to, right, the different blocks or records that contain this value 2, and so on. So I have a level of indirection that you're using to handle the duplicate values. Okay, this is a non-dense or a sparse index because I don't have an entry per record, and it uses a level of indirection. You could also have, this is the preferred method, and this is the one used in practice in most database management system, but you could also use here an index which is dense. You create a value per record, right? So repeat values, but that makes binary search very hard, and the index size becomes large, so it becomes really much worse in terms of performance. Okay, so this is really the ideal way to do this. Questions about this one? Okay. How about searching? So how do I find the record? All I have to do is do binary search on this, follow the pointer, right? Let's say it's the value 4. I follow this pointer, that gives me this block, follow the pointers inside this block to get the records. What about insertion and deletion? What do I have to do? Easy peasy, right? I put, you know, the record, the new record anywhere, so a new block, for instance, and then just put the right pointer. So if it's, let's say, the value 3, I'll create a new block, put the record with value 3 here, and go here and update this block pointer to add a pointer to this block. Yeah, so it's not super difficult. Deletion would be just you remove the pointer from here. Yeah, so it's not very difficult. Okay. So summary, and then we're done. Okay, so if the index field is a key and the file is physically ordered on the indexing field, then it's a primary index. Yeah, the type of index you can create is a primary index. If the indexing field is non-key, so it has duplicate values, and the file is physically sorted on this indexing field, then you create a clustering index. If the file is not sorted on the indexing field, then it's a secondary index, whether it's a key or non-key. Okay. Properties of the index types. So you have primary, clustering, secondary, and secondary non-key. Number of first level index entries. In the primary, it's equal to the number of blocks in the data file because I'm doing block anchoring. So there is an entry per block in the primary. In the clustering, it's the number of distinct index field values. Yeah, remember that I only look at have an entry per distinct index value. For the secondary, it's the number of records if I'm doing on a key, and the distinct values if I'm doing on non-key, right? The third option at least. Primary keys are non-dense, clustering indices are non-dense, whereas secondary on a key is dense, and secondary on non-key is either dense or non-dense, depending on which option you use. Okay? So block anchoring, right? Basically, this is what we do for primary, meaning what? Meaning that I store only the entry in the first block. Okay, clustering is yes and no. Yes, because you could do this if you're doing this per, remember this option where we reserve certain blocks for a particular value, then I'm doing some block anchoring because the entry or the pointer will point to the to a particular the value of the first value of a block, and it's no in the other case when we don't have a reserved block per value. Okay, and secondary indices do not do, of course, block anchoring because they really have pointers everywhere. Okay, let's sum this part up. Next time we'll talk about indices on multiple attributes, multi-level indices, and how to create indices using SQL. Any questions? Okay, I'll post the recording of the lecture as always on Moodle, and we talk on Thursday. Thank you. Yeah, bye bye.